So the question next is, why do some isotopes undergo radioactive decay and other isotopes not? It has to do with the stability in the nucleus. If you look inside the nucleus, there's a certain number of neutrons and protons, and you can calculate the ratio of neutrons to protons. Here's a picture from the textbook that shows little dots for isotopes that are stable, plotting number of neutrons versus number of protons. This is when the number of neutrons equals the number of protons. So when elements are very light, the stable isotopes seem to cluster around this value where the protons and the neutrons are equal. As the elements get heavier and heavier, the stable isotopes have more neutrons, and this band of stability goes away from that ratio where n is equal to z. So the key is, if you have an isotope and you calculate where it is on this graph, if it's in this region of stability, then it's most likely not going to undergo a radioactive change. However, if it's off that band, it could either be here at point A, which is too high, or it could be below the band of stability at point B. The different types of radioactive decay that we've already seen, if you go through and look at the parent and the daughter, and you calculate how many neutrons each one has, how many protons each one has, and look what happens to the ratio, that's what's worked out for you on this table. So alpha decay makes that ratio go up, just like positron emission and electron capture. The only one that makes that ratio goes down is beta decay. And remember, gamma radiation has no mass, so there's no change in the number of neutron to proton ratio. So if you're at point A, you're too high, you need to decrease that ratio. So beta emission is a possibility. Point B, it's not stable because it's too low. The element can become more stable by moving up. So there's more possible choices that will make that ratio increase. A similar sort of graph is shown in this picture. That this shows the parent and the daughter, and we want to figure out what that reaction is. So we want to write out the balance reaction starting from this graphical form. So key thing to keep in mind when you're doing this, remember that the isotope symbols do not have the number of neutrons in there. The isotope symbol always has the mass, which is number of neutrons plus the number of protons. So if we look at the parent, in this case, the parent has 44 protons. The atomic number is 44, so that's ruthenium. The parent starts with 46 neutrons. 46 plus 44 gives a mass number of 90. So this is ruthenium 90. If we do the same thing for the daughter, we can see that the daughter ends up with 43 protons, 47 neutrons. So the mass number hasn't changed. If this came from emitting one other particle, we can figure out what this is by making the mass numbers conserved and making the atomic numbers conserved. So 90 is equal to 90 plus 0, 44 is equal to 43 plus a positive 1, and this is a positron emission. However, remember, positron emission always goes with electron capture, so this could also stand for a different reaction. Same parent, same daughter, but by capturing an electron, we can write two different reactions for this same graphical representation.